Good morning, or yeah, good morning, second, third, and fourth period AB. Let's go. Here's our warm-up for today, Monday, February 1st. We're asked to find the antiderivative of 1 over x squared minus 2x plus 2. And this is using what we learned on Friday, in that we are going to do completing the square with the denominator. When we do complete the square with the denominator, we're going to have x squared minus 2x blank minus the same blank, which is that plus 2 there. Okay, it always has to be half the b term squared. Half the b term squared. Well, our b term is -2. Half that would be -1. -1 squared will give us +1. And that +1 there also has to get subtracted out here. So then that new function that we're finding the antiderivative of, or doing indefinite integration of, will be 1 over this whole parentheses. Once we added that, we made it become a perfect square trinomial. So it's now x squared minus 2x plus 1 is just x minus 1 quantity squared. So we have -1 and +2, which is just going to be a +1. So I could have the dx in there. Okay, well, now this does look very similar to inverse trig. We have 1 over a variable squared plus 1 squared. Variable squared plus 1 squared, where this is u equals x minus 1, and this is a equals 1. So this will end up equaling arctangent of u over a, which would just be x minus 1. No e. Okay, well, I'm going to do the lesson for today first before I cover people's problems. Several people asked me to do some problems, which is awesome. Glad you are doing your work, and glad you were also going to ask me questions. So we're covering today is the second fundamental theorem of calculus, or part 2, or it's also just a debate over which one really is part 1 or part 2, or the first or the second. There's really just two consequences, two ways to use the fundamental theorem of calculus, and we're going to the second one we're going to cover today. And I'm going to show the second fundamental theorem of calculus by using the first fundamental theorem. Now, the first fundamental theorem of calculus was just how to do definite integration with functions. So we are trying to take the derivative of that integral. We're trying to take the derivative of that integral. So that's what d dx is, which we learned last semester. The derivative of the integral from 1 to x of t squared dt. So in order to do so, we're going to find the definite integral from 1 to x of t squared dt, and then take that derivative, see what happens. So first we're going to take the integral of 1 to x of t squared dt. So first the antiderivative of t squared, well, that would be t cubed over 3. Evaluated from 1 to x. Okay. And next, yes, that's still going to be there. Now we're going to plug in the upper and lower limits. So that becomes x cubed over 3 minus 1 cubed over 3. Okay, so we did the definite integral from 1 to x of t squared, and now we're going to take that derivative. If I take the derivative of the inside, I am going to end up with, well, the derivative of x cubed over 3 will give me x squared, and the derivative of 1 cubed over 3, well, that's 0, so we get x squared. That's pretty cool. We get the derivative just is the original function there. Well, let's see if that happens again. So same idea here. We are taking the derivative of that whole integral. So I'm going to do the same process. So integral of cosine. Well, what derivative produces cosine? That would be sine. So we have sine of t evaluated from pi over 6 to Now we plug in our upper and lower limits. Derivative of sine x minus sine of pi over 6, that would be 1/2. And now we take the derivative. Well, derivative of sine, that is cosine. Derivative of 1/2, that is 0. So we ended up with cosine of x. Okay, and so essentially the same thing happened here as what happened on the first time, that when we took the derivative of the integral, and these two things were definite integrals from a number to x. We had definite integrals from a number to x of some function of t dt. And when we took the derivative of that definite integral from a number to x of a function of t, we ended up just getting the function of x, which that is the fundamental theorem of calculus, which just shows that derivatives and integrals are inverses of each other. That when we take the derivative of this integral, we are just going to get a function as is, f of x. Now, let's look at one slight difference here on this one. The difference on this problem here is they've switched the limits. They've switched the limits. And so I'm going to switch the limits to be like what we had before. Actually, you know what? I'll show it the whole way. We're taking the derivative of integral of t squared. Again, will become t cubed over 3, evaluated from x to 4. And that would equal the derivative of, we would now plug in our upper and lower limits. So that would be 4 cubed over 3 minus x cubed over 3. Derivative of the first would be 0. Derivative of the second term would be a negative x squared. So the difference this time is that negative. It became the same function, but because the limits were flipped, the sign was flipped. Because the limits were flipped, the sign was flipped, which should make sense based on our definite integral rules. That should make sense based on our definite integral rules. Another way I could have done this problem here is I could have just done derivative of, I could have just flipped them and put a negative in front. So the integral from 4 to x of t dt. And we just learned previously that if I take the derivative of a integral from a number to x of f t dt, that'll just give me f of x. So if there's a negative in front, it would just be negative of the f of x. And so that is the idea here, that if we have the number on top, the x on bottom, it'll end up being negative f of x. So the derivative of a definite integral from x to a of f of t dt is just negative f of x. Okay, well now, let's see what happens when the upper limit isn't just x. Here, the upper limit isn't just x. Our upper limit here is x squared. Our upper limit here is x squared. So our upper limit is a function of x, not just x. Our upper limit here would have a derivative of something other than just 1. And so we're going to discover this same way we did the other ones. I'm going to do the definite integration. So antiderivative of cosine is sine from pi over 6 to x squared. And we plug in the upper and lower limits, which will give us derivative of sine of x squared minus sine of pi over 6, which is 1/2. And now we take the derivative. And when I take the derivative of this, that is going to, we have to do chain rule here. That x squared is a function inside of sine. So we're going to have to do chain rule when we take the derivative of the sine of x squared. So it'll be cosine of the inside x squared times the derivative of x squared, which is 2x. So we will get 2x cosine of x squared. And then the derivative of the negative 1/2 is 0. So that's what we get there. So what ended up happening on this one is this function up at the top, the x squared, it got plugged into the t. Same way as our x's did up in the other versions of the fundamental theorem of calculus. They end up giving us cosine of x squared, but then what also happened is we ended up multiplying by that function, its derivative, because of chain rule. So if we're taking the derivative of a definite integral from a number to g of x, so not just x, a function of x, then it will end up being f of g of x. And I get that aspect because of that entire g of x goes in the f spot as it did here with that x squared going where the x was. But then what else ended up happening was that we multiplied by the derivative of that inside function. So it ends up being multiplied by g prime of x. And that's the chain rule version of the second fundamental theorem of calculus. So if we apply some of this on these two problems down here, we're taking the derivative of the integral from 3 to x, the square root of 1 plus t squared. And this is actually fairly simple. I don't need to do the full demonstration as what I had been doing. I have just applying the second fundamental theorem of calculus. All that ends up happening is it just becomes the function as is with x in there. So it's going to be square root of 1 plus x squared. Or on this one, it would become tangent of x cubed, because the derivative of an integral from a number x is just the function as is. Now, these two are a little different. Here we're taking the derivative of the integral from -1 to x cubed of 1 over 1 plus t. Well, because it's x cubed, that is a function of x. So similar to my chain rule example of fundamental theorem of calculus, that whole x cubed does get plugged into the t spot, very similar to a and b, but then we also have to multiply by the derivative of that function. We also multiply by the derivative of that function. So this will end up being 1 over 1 plus x cubed. And then because of chain rule, we have to multiply by the derivative of that upper function, so by 3x squared. And I could have written it as all one term as 3x squared over 1 cubed. And on D, something very similar happens here to what we just did. Taking the derivative of the integral. When you take the derivative of the integral, they just give you the function as is, but our upper limit isn't just an x. So that upper limit does get plugged into the t spot, but then it's also going to have to multiply by the derivative of that upper limit. So this will get multiplied by cosine. I'm going to have cosine of x in front because that's the derivative of sine, and then times the cube root of 1 plus sine squared of x. There we go. And that is it on the second fundamental theorem of calculus. And what I will do for the rest of this time is go over some of the problems that people have asked me about. We still have like 37 minutes left. I don't know if I'll take up that much time. But first, someone asked me about section 31, numbers 11 through 13. Section 31, numbers 11 through 13. Good. So here they are here. So on section 31, 11 through 13, one important aspect of all three of these problems is that they are even functions, And when we did section 31 last Monday, I did go over the end of class, something attributes of even and odd functions. And a nice attribute of even functions is that they're symmetric across the y-axis, which is going to mean that for an even function, if you're taking the integral from negative a to positive a of f of x dx, since it's symmetric across the y-axis, that will end up meaning the exact same amount of area is on either side of the y-axis. The exact same amount of area is on either side of the y-axis. So then, the integral from negative a to positive a would just end up being, I don't want to do that, the integral from 0 to a of dx 2 times the integral from 0 to a of f of x dx. Because you would have the same amount of area on the right side of the y-axis as on the left side. So then just 2 times the area on the right side would be the entire area from negative a to positive a. So that is one attribute that is being used on these 3 problems. And another attribute that's being used on these 3 problems is that they're all u sub problems, because we have a function inside of a function. Got a function inside of a function. So on number 11, I'd call that inside piece 3x my u. So we'll have u equals 3x. Du would then be 3 dx. Got no other 3 here, so I'm going to divide by 3. Something else we need to do here, because definite integration with u, so we need to change the limits. So u of negative 3, that'll be negative 9, and u of positive 3 will be positive 9. Now we can rewrite the integral as 1/3. Right, yeah, as 1/3 the integral from negative 9 to positive 9 of f of u du. Now, all the integrals they give us up above are integrals from 0 to 1, or 0 to 3, or 0 to 9. So to be able to use those, I want my lower limit to be a 0, which based on the rules of even functions, I can do that here. And I can make it be the integral from 0 to 9 of u du if I just multiply it by 2, because that's what would end up happening. And then the integral from 0 to 9 of f of u du, they already told us what that was. They told us that right here. The integral from 0 to 9 of f of u du is 12. So we have 2/3 times 12, which is 8. The fact that these have x's and these have u's, that doesn't change anything. Like, it's still the same f function and the same limits of integration. As long as it's the same function, same limits of integration, the fact that we changed the name of the independent variable doesn't affect that. So it is 2/3 times 12, which is 8, that one. And you would do the other ones very similarly to what we just did there. Number 12 is pretty much exactly the same. So I'm going to skip 12 since it's pretty much the exact same method as 11, and I'm going to do 13, slightly different than 11 and 12. So on 13, we're going to do some of the same stuff here in that we will do u substitution. So I am going to call u equal to 3x like before, and du would then be 3 dx. We would divide by 3. Yeah, we need to get our new upper and lower limits. So u of 1 is 3, and u of 3 is 9. Okay. But u of 1 is 3, u of 3 is 9. So that will then become 1/3 the integral from 3 to 9 of f of u du. Okay. Well, one problem has now arisen. They didn't give us an integral from 3 to 9. They did give us the integral from 0 to 1, 0 to 3, and 0 to 9. So 0 to 1 probably doesn't have anything to do with what we have here, because, well, what we have here doesn't have anything to do with 0 or 1. But we have 3 and 9 as our upper and lower limits. And we have 2 integrals here. One's from 0 to 3, another one's from 0 to 9. So the idea, what could we do with these two integrals to end up getting that one? What could we do with these two integrals to end up getting that one? Well, this one, 0 to 3, that's giving us the area starting at 0 and ending at 3. And then ending all the way at 9 is this one. So this area of 12 is telling us the area is all the way from 0 to 9. And this area here from 0 to 3 is telling us the area from 0 to 3. So we have the area from 0 all the way to 9. We have the area from 0 to 3. We want over here the area from 3 to 9, that leftover piece. So what we're going to do is we're going to subtract these two. I have 1/3 out front. I'm going to take the integral from 0 to 9 of f u du and subtract the integral from 0 to 3 of f u du. The integral from 0 to 9 minus the integral from 0 to 3 will give us the integral from 3 to 9. And so then that will be 1/3 of 0 to 9 was 12 minus 0 to 3, -6. Okay, well, 12 minus a -6, that's really plus 18. 1/3 of 18 is 6. Yeah, there we go. Awesome. And then 12 is really just like 11. So here we go. That's those three problems from section 31 that I was asked about. Next, we're going to go to section 32. Section 32. I was asked about a lot of problems on section 32. Which page do you need? Okay, this one right here, 8. 8 was the next one I was asked about. Oh, one reminder. I did say that on section 32, I'll just put it right here since this is scrolling really slowly. I did say that for section 32, entirety of section 32, it's evens only. You only have to do the evens on all of section 32, and I'm including the inverse trig page, like the inverse trig page, that last page, page 9 in the file. It would be the 4th page in the packets. But the inverse trig page also evens only. So evens only on all of this because there's tons of problems. It's unnecessary. I mean, you feel free to do the odds if you want to, but it's unnecessary. You don't need to do all of them. Evens only is what's required. Now, 8. 8, I get the confusion why some people would have asked for 8 because there's multiple ways to do 8 correctly. Even when I first looked at 8, how I want to do this problem is very similar to how some of the people asking me about this problem did it, and they're confused why the answer key has a slightly different answer. And really, it's because of the natural log in this problem of why we can have two different correct answers that are equivalent and look different. Because of the natural log and the natural log properties, there's two different correct answers. Probably more than two, but there's different correct answers, different correct ways to do this. I'm currently assuming that some of you who are asking about this probably did it right, but you're confused why it has a different answer in the answer key. So I'm just going to go about this the way I would want to do this, and I'm going to do it, I think, the way you would want to. I've looked at the key, and I don't want to do it the way they did. Because I wouldn't automatically think what they did. Let me go ahead and explain. Is in this denominator, they're all even. They're all even in this denominator. So one thing you could do is you could factor out a 2 out of the denominator, out of entirely in front of the entire integral. So essentially, you're factoring a 1/2 out in front of the entire integral, and that's completely okay. That's what they did on the key. And if you go that method, the next step would be the actual first step that I'm going to do. But you would end up getting an answer that is equivalent but different to the answer that we're going to get. So I would prefer, because you are probably not going to think of doing that. I don't automatically think of doing that because that's not one that's obvious that you can factor out. So I'm going to take this entire bottom and I'm going to treat it as u. So we have u equals 2x squared plus 16x minus 6. And if that's our u, then du would be 4x plus 16 dx. 4x squared plus 16 dx. Okay, well, what are the things that we need to replace? We have this x plus 4 and dx. Got that x plus 4 and dx. So I want to change this 4x plus 16 into the x plus 4. So what am I going to do to get that? I'm going to divide by 4. Because once I divide by 4, I then get that 1/4 du is x plus 4 dx. Okay, awesome. So x plus 4 dx will get replaced by 1/4 du. So then that gives us 1/4 integral of 1 over u du. Well, then that becomes 1/4 natural log of the absolute value of u, which would then become 1/4 natural log of the absolute value of 2x squared plus 16x minus 6, then plus c. And I know for sure that the answer key probably has something a little different than that. And I'm also assuming that a lot of you probably got something similar to what I got. And so you're confused why this is different than that. And if you got this, then you did do it a correct way, which is awesome. But this is slightly different because I could factor that 2 out on the inside. And if I was to factor that 2 out on the inside, that would end up being natural log of 2 times the x squared plus 8 minus 3. Well, then when you have natural log of things being multiplied, then that could be separated to be something being added. And you would have natural log of 2 plus natural log of that, and then plus the c. Well, then we have some random constant. Well, then c could be considered part of that random constant. And since we don't know what c represents, it doesn't matter that we didn't factor that out or having that factored in. So if you factor the 1/2 out at the beginning, or if you don't factor the 1/2 out, as long as if you have the process right, you got the right thing here. This is a correct way to do that. But what they have is also correct. It is equivalent. The 2 equivalent answers because of natural log properties. Okay, next one I was asked about was number 20. Yeah, number 20. Oh, there it is right there. Okay, well, we have integral of e to the x plus e to the negative x quantity squared. Okay, don't see how we could do u substitution here, because if I chose the inside of that parentheses to be u, I would need its derivative also there somewhere. Well, its derivative would be e to the x minus e to the negative x, and well, that's not also in that problem anywhere. So what my thought is, the easiest way to do this problem is we would actually square that. What I mean is we have e to the x plus e to the negative x getting multiplied by e to the x plus e to the negative x. We're going to actually multiply that out, FOIL it. So e to the x times e to the x, well, that would be e to the 2x. Because the exponents would add, because it's the same base. And x plus x is 2x. Okay, then the outside would be e to the x times e to the negative x. The exponents would add, and x plus negative x would be 0. Same thing would happen on the inside. E to the negative x times e to the positive x. The exponents would add, which would become e to the... let me put it this way. No, it would become e to the 0, which is 1. Never mind. It would become e to the 0, which is 1. E to the x times e to the negative x that would become e to the 0, which is 1. You'd have another 1 in the middle, so we end up with plus 2. So you probably got confused on that. So let me show that what I mean again. So what's happening is this e to the 2x, that came from e to the x times e to the x. E to the x times e to the negative x, that would become e to the x minus x. Well, x minus x is 0, meaning e to the x minus x, that is just 1. And then the inside ones, same thing's happening. E to the negative x plus x, making that whole thing 0. So that's 1. E to the 0 is 1. And then the last terms, that'd be e to the negative x times e to the negative x, which would be e to the negative 2x. Okay. So we're really doing the integral of e to the 2x plus 2 plus e to the negative 2x dx. There we go. So all I did there was we multiplied out the e to the x plus e to the negative x getting squared. And now take its integral. In an antiderivative of e to the 2x, I'm going to divide by the new power. I'm not going to fully formally do u sub. It will become 1/2 e to the 2x. And then antiderivative of 2 is 2x. And then antiderivative of e to the negative 2x, that'll become negative 1/2 e to the negative 2x plus c. Okay, and then we remember 20. Oh, going pretty quickly. We still got 20 minutes left. Okay, then I was asked several questions about several inverse trig problems. Okay. First question was about number 11. Well, as a reminder, you only have to do evens here, but I will still show 11 because I'm pretty confident I gave you that formula wrong, actually. And I remembered it wrong because we don't really need it that much. Because having the x in front of the square root, makes this one a inverse secant problem. Having the x in front of the square root makes this an inverse secant problem, where just u is the x and a is the 3. And I did give it to you wrong because inverse secant is also supposed to, just like inverse tangent, have a 1 over a in front. Inverse secant, just like inverse tangent, is supposed to have a 1 over a in front. And I forgot that because inverse secant is almost never used. So this one would end up becoming 1 over 3 secant inverse of x over 3. And I forgot the 1 over 3 on last Thursday's video because of, well, inverse secant's almost never used. Okay, well, next I was asked about 12, which is understandable and possible. So let's go over 12. Okay, well, on 12. So 12, we see two problems. Two problems being that we have x and a 3 on the numerator. We have an x and a 3 in the numerator. See, having square root of a number minus x squared in the denominator, especially based on it being an inverse trig worksheet and having just discussed a lot of inverse trig kind of problems, makes me think it's an inverse sine problem, but inverse sine would not have an x on top. Inverse sine would not have an x on top. So that x on top prohibits it from only being an inverse sine problem. Having the x on top might make us think that it's a normal u sub problem. Well, if I was to do u sub and have the 16 minus x squared be my u, well, then the 3's in the way. Because if it was a normal u sub problem, I should only have the derivative of u being what's left over. And then I still got that plus 3 that's causing a problem. So the way that I'm going to solve both problems is I'm just going to make them two separate integrals. Because that x being on top makes me think it's a normal u sub problem. That 3 being on top Makes me think it's an inverse sine problem. Well, I'm just going to split them up. So we're going to have two separate integrals, one where we have x on top over square root of 16 minus x squared, then plus integral of 3 on top of square root of 16 minus x squared dx. Now I can treat them separately just like I was just discussing. No, one of the latter ones requires this again. I'll go ahead and mention which one. Which one was it? Well, it would be 15 and 16. That would probably both need this. Yeah, 15 and 16, you'd split it up. 15 and 16, you'll split both of them up. Okay. And then 15 and 16, so you'd split them up. What am I writing? Just go ahead and write this down for y'all. You'd split them up into separate integrals. And then as well as both of these will also require completing the square. But again, you don't have to do 15, but that's what 16 would require. In 16, you would split it up and you do completing the square. Very similar to some of the stuff in Friday's lesson. Some of the stuff in Friday's lesson. Okay, well, back to 12. Let's finish 12. So on this first one, we have x over square root of 16 minus x squared, and we would do some normal u sub there, calling u 16 minus x squared going to du negative 2x dx. Well, I got an x dx, so I'm just going to divide that by negative 2. And so that first integral will become negative 1 integral of this particular scenario that I'm talking about right now. There was a lot of people that on last Tuesday's test, well, no, it ended up being Wednesday because of the SAT. But on Wednesday's test, there was a lot of people who, when they were doing U sub for a problem like this, and there was one just like this, when they replaced the U here, they had the wrong exponent. They either forgot the square root or forgot the negative, or both. Like all sorts of issues with people replacing this U substitution on this problem. But we're having that 16 minus x squared, which is inside the square root and in the denominator, that is becoming our U. So that U needs to have the same exponent as what that phrase has. So it needs to be a negative 1/2 exponent. And then we could take the antiderivative of that. The power would go up 1, and we'd multiply by the reciprocal of the new power, meaning multiply by 2, because the power is going to go up to positive 1/2. We'd multiply by 2, so it'd be 2u to be 1/2. So it's going to be negative square root of 16 minus x squared. Okay, so that's the antiderivative of that part. I'll have plus. Now, the rest of it. Well, this piece here, I could factor out that 3, and we'd have integral of 1 over square root of 16 minus x minus x squared dx. And now this looks just like the inverse sine, where we're going to have here is the x, and a would be the square root of the number, so it's going to be 4. But in inverse sine, there's no 1 over a in front. That's inverse tangent and inverse secant. So no 1 over a in front, so this will just be plus 3 sine inverse of x over 4, and then plus c. And so that's how we get number 12. Yeah. 14 and 16, pretty sure both of those require, actually, I think all three of these require completing the square. Maybe I should have had these after completing the square lesson. Oops. Okay. So that's 11 and 12 people asked about. People asked about 15 and 16 as well. Okay. Well, I'm going to skip 15 because it's odd, and I'm running out of space too. I'm running out of time. Let's see. We've got 11 minutes left. And Maria just now asked another question. Sorry, it's probably not going to happen, Maria. Put on the next video. I didn't mention earlier, I'm making this video on Sunday evening right now. Okay, so same idea. First thing, like on 12, I'm going to split this up into the integral of 3 over the square root of 10x minus x squared minus 9 dx, and minus Now, one other thing. Before I do that, let me show you, because there's something else I'm going to have to do. So let me explain what that is. So just like the previous problem, when we split it up, one of them is going to end up being U substitution, and the other one's going to end up being an inverse trig problem, really an inverse sine. So one's going to be U sub, one's going to be inverse sine. So for the U sub, that means what's inside here will be our U. So if that is my U, then I'm going to have U equals 10x minus x squared minus 9. Well, if that's my U, then du is 10 minus 2x. Okay. That's close to that. That is close to that. So currently, U sub will not even work with my thought of splitting it up. I would need that to be a 10 minus 2x. And I really should have had this after the next lesson. So what I mean by that is, well, in the next, in what we covered on Friday, there was a example or two of, no, there's one or two examples of essentially adding 0. There's one or two examples on adding 0. And what I mean by that is we want to add a certain number, but so we don't change the value of the entire integral, we're going to also subtract that same number. So I want that to read 10 minus 2x. Well, in order to do so, I need to add 7 to that. So we're going to add integral of, we have 3 minus 2x. And then so that's not a 3, I want it to be a 10. I'm going to add 7. Well, so I don't change the value of the integral. Since I added 7, I need to subtract 7. Oh, the square root of 10x minus x squared minus 9 dx. Now that I did that, now I can split it up exactly as I want to, in that I want the 10 minus 2x together. So we have the 3 and 7 will become the 10. So we're going to have 10 minus 2x over the square root of 10x minus x squared minus 9 dx. And then that one will just be some basic U sub. And then what we have left over on top is that minus 7. So then we're going to have minus, and I'm going to go ahead and factor the 7 out, 7 times the integral, 1 over square root of 10x minus x squared minus 9 dx. And then that first one will be U substitution, which we've already figured out what the U and du will be. 10 minus 2x dx. That is our du. U is what's inside the square root. So that one ends up becoming the integral. I don't even have to do any manipulation to that because we have 10 minus 2x dx. So it's just going to be integral of u to the negative 1/2 du, which would become 2u to the 1/2, which is 2 square root of 10x minus x squared minus 9. Then we're going to have minus 7 times whatever that thing becomes. And this one we will need completing the square for. So what I'm going to do, I'm going to factor. We did one like this on Friday. I'll factor the negative out of the x squared part. It'll become negative parentheses x squared. And then that would end up being a minus 10x. I'm going to leave the minus 9 alone, not changing the 9 yet. I'm going to have the blank in parentheses, another blank, the minus 9. Okay. So now I need to figure out what goes in that blank. What's going to be half the b term squared? Half the b term would be negative 5 times 5 squared would be 25. Okay. Well, that negative is getting multiplied by the entire parentheses. So it's really a negative 25. Since that's really a negative 25, I actually want to add 25 instead of subtract it. Okay. So then that means this will be minus 7, the integral of 1 over. When we do the completing the square, it'll now be square root of this parentheses factors into x minus 5 quantity squared. Factors into x minus 5 quantity squared. And I'm going to move it to the right, and the 25 and the minus 9 combines to be a 16. So then that gives us 16 minus this parentheses factors into x minus 5 quantity squared. And we have the dx. So this parentheses factored into x minus 5 squared, that negative went to right there. 25 minus 9 went to right there. And now it's just an inverse sign problem where the u is x minus 5. But we don't have to do u substitution because its derivative is just just 1, and the a equals 4. So the antiderivative of that then would be sine inverse of x minus 5 over 4. And then plus our c. Okay, class is almost over. I'm going to check real quick. Really hope I didn't do that wrong. I did not. Awesome. Yeah, 12 and 16 were just like that. Yeah. Okay, and then was I asked about any others on here? 15, 16. I went over 16. You don't really have to do 15. I went over 11 and 12. Oh, I was also asked about 26. We got 3 minutes left. I'll do 26. Scroll. What is happening? Don't do that. Okay. Let's change colors. So on 26. So what I'm going to do for 26 is I'm going to do just some basic U substitution. I'm going to do some basic U substitution on U on 26. Do I need to? You know what? We don't need to do that. We don't need to do that. And we don't need to do that because yeah, it is definitely going to be basic use of. It is definitely going to be basic use of. Or I'm going to choose the entire denominator to be my u. I'm going to choose the bottom to be my u. So u will equal 1 plus e to the 2x. And then the derivative of that, derivative 1 is 0. Derivative e to the 2x will be 2e to the 2x dx. Okay, well, we have e to the 2x dx, so I'm going to divide that by 2. Okay, so e to the 2x dx will be replaced by 1/2 du. So it will be 1/2 integral of, I am replacing the entire bottom with u and the e to the 2x with du. So it will end up being 1/u du. Okay, we need to also replace our limits now. And so that will be u over limits 0. So u of 0, well, that would be e to the 0, and e to the 0 would be 1. So 1 plus 1, that is 2 for the new lower limit. And then u of 3, u of 3. U of 3 would be, that's annoying. Well, that would be e to the 6th, then plus 1. E to the 6th plus 1. So e to the 6th plus 1 is the new upper limit. Now to evaluate this, antiderivative 1 over u will be the natural log of absolute value of u. So 1/2 natural log of, I don't need the absolute value because the upper and lower limits are both positive. Natural log of u, evaluated from 2 to e to the 6th plus 1. Now we plug in the upper and lower limits. Okay, so it's been 52 minutes. Let me just finish this real quick. That'll be natural log of e to the 6th plus 1 minus natural log of 2. And there we go. That's how we get that answer. And they seem to have, yeah, they went one step further. They went one step further in the answer key. Since we are subtracting 2 natural log terms, you combine them into just 1 natural log term. And subtracting 2 natural log terms, when you put them together as just 1 term, divides the arguments. That would divide the insides. So we have e to the 6th plus 1 over 2 on the inside of the natural log. Okay, there we go. I think I went over every question people asked. Awesome. Well, just so you are aware, I have tested negative. I don't have coronavirus. I'm not sick, but they won't let me come back. And some of you know that experience as well. Been forced to quarantine and not able to come back till it's been 14 days since exposure. So it's very frustrating. I don't like it either. But have a good day. Keep track of your assignments and your work and continue to ask me questions if you have any. Okay, and tomorrow we'll be on section 28. Tomorrow, section 28. Okay, have a great day.